our second lecture, dividing it up into two parts as usual. We are going to talk about matrices, one of the or about a matrix. Matrices is a plural of matrix, which is an object which is of great importance to mathematics, because it can be later on viewed as a function. One might think that matrices is nothing but a array of numbers, a rectangular array of numbers. Just like here you see a matrix A, which has some 3 columns. Also we can think of it as having 3 rows. Usually it can have more rows and less columns, more columns and less rows, and all those things. So it is a rectangular structure with rows, some number of rows and some number of columns. But it has huge implications and huge applications in many parts of science, technology, economics, business management, and so on and so forth. So, keeping aside that little pep talk, I think we should understand that apart from viewing this matrix A, say, as just a rectangular array of numbers, we should rather view it, because we already know about vectors, as a collection of 3 column vectors 1, 4, 7, 2, 5, 8, 3, 6, 9. That is another way to view it, but I am not advocating that that is the best way to view it, but that will turn out to be one of the most profitable ways to view it. So, here I write it in a more generic fashion, that the entry in the first row and the first column. So, here if I just look at the number 2, for example, it is in the first row of the matrix, but it is in the second column of the matrix. So, we always say that element would be written as a small a I j, where I represents the row number and j represents the column number. So, it is always row into column format. So, here is a matrix which has 2 rows and 3 columns. So, we call it a 2 into 3 matrix. So, if there are m rows and n columns, we will call it an m cross n matrix. So, if m is equal to n, we will call it a square matrix, because it will now look like a square, not a rectangle. Let us give some examples of important square matrices, for example. So, we are just writing in terms of 3 by 3 matrices. This is an approach which Gilbert-Stein has taken in his latest book, Linear Algebra for Everyone. But I think it is very important to tell about some important class of matrices. I include some more than what he has told us, but for example, this is identity matrix. An identity matrix where the first entry of the first row, ith entry of the ith row is 1 and everything else is 0. Ith entry of the ith column is 1 and everything else is 0. So, that is called the identity matrix. You will see its usefulness, it is a key matrix. Another matrix is a diagonal matrix, which almost may suddenly look to you as quite similar to the identity matrix, but instead of having 1 as the entries in the diagonal, these entries A I, that is A 1 1, A 2 2, A 3 3 are called diagonal entries, when I am matching they have the same row and the same column. So, but here the diagonal entries are 1 7 6. So, it cannot be called a identity matrix. So, as we will later show that identity matrix is a matrix which, when acts on a vector, that is when you multiply it with a vector, it does not change the structure of the vector. And we will soon play a bit later on with identity matrices and develop what are called, or rather talk about what are called permutation matrices, which switch the positions of the components of the vectors. Here is a lower triangular matrix. So, you have a diagonal, so diagonal element can be anything, and anything below the diagonal would be 0. Any entry which is below the diagonal would be 0, and there can be similarly upper triangular matrix where anything below the anything above the diagonal is 0. I hope I am giving the right terminology, but as I check it up, I must also check it up, because I am very bad with maybe lower triangular, maybe should be called lower triangular, upper triangular, or maybe this should be called lower triangular and that could be called upper triangular. Maybe I have made a mistake, possibly I am bad in this number. So, these can be called triangular matrices, means either the upper part of anything above the diagonal all the entries are 0, or anything below the diagonal all the entries are 0. Maybe this would be called upper triangular and this would be called lower triangular, whatever, whichever. A matrix is called similar. So, you see any matrix is represented as Aij. I did not write it here, but here I have written Aij n cross n matrix. So, this is a square matrix. So, in general a matrix A is written in Aij. If it is symmetric, then Aij is equal to Aj. That is, if I switch the column and row, because it is square. So, I can switch the column and row. So, then they will have the same elements, that is A12 is equal to A21, A32 is equal to A23, right, that kind of thing. Then there is a skew symmetric matrix. So, skew symmetric matrix just has the opposite thing. There Aij, they are all square matrices, is equal to minus Aj. So, here there is a crucial fact that if I, because this is true for all Ij, right. If you have here Aii, for example, you will have Aii equal to Aii, it does not matter if you switch I with I, that makes no sense. But here if you have Aii, you will have that should be equal to minus Aii, and which will give us all the diagonal elements to be 0. So, a skew symmetric matrix will have this property, and also it will give me all the diagonal elements to be 0, and that is the interesting part. Skew symmetric matrices do play certain important roles, but that is possibly not much needed for our study. Symmetric matrices will play a very key role. We have focused on matrices with real entries, that is one of the key things. We are not talking about what about if I put complex numbers in, that is what about if I have a collection of complex column vectors basically, then what would happen. So, we will not discuss it right now, we will take it in a detour at the end. We will now talk about only complex, the only real entries, and the scalar that we will use to do some more playing in with the matrix will be only real numbers. So, that is what we need in economics, that is what we need in a huge gamut of applications. Sometimes in engineering you need complex matrices, electrical engineering, sometimes in physics of course you continuously need complex matrices, but because we are doing a different kind of mathematics or a different kind of scenario where we are talking about economics or talking about things which would be used in operations research, for example, then there things can be just we can just keep on focusing ourselves on the real matrices and having scalars drawn from which are just real numbers, and then yet profitably do a lot of things and would be able to apply when the real scenario comes, when we need to really apply. So, consider 2 into 3 matrix 1 3 4 6 7 9 or 1 6 3 7 4 9, whichever you want to call it. So, it has 2 rows and 3 columns. So, I always view it as a collection of columns 1 6 3 7 4 9. You need not view it in that way, of course, it is up to you, but I would like to view it in that way. What is A transpose? A transpose means rows will now become columns and columns will now become rows. So, whatever was 1 6 as a column, it will become a row. So, I take the transposes of the columns or transpose of the row, that becomes the first column. The first transpose of the first row, which is the column which now becomes a column vector 1 3 4, becomes the first column of the new matrix, and the second row is 6 7 9, whose transpose is 6 vector 6 7 9, that column becomes the second column. So, when I take a transpose, a 2 cross 3 matrix now becomes a 3 cross 2 matrix, because the rows and columns have changed. So, you just have to change the row number with the column number and column number with the row number, that is the key idea. So, if A is an m cross n matrix, we in short we write A is Aij m cross n, and A transpose is nothing but A j I n cross m, because j was indexed over n 1 to n and I was indexed from 1 to m. That is why this is instead of wherever in place of A j I, wherever there was A I j, for A transpose in that same place there should be A j I, that is it, that is the idea. That is, rows and columns have changed. Any column vector, we will always write vectors as column vectors unless we are specifically meaning row vectors. Sometimes while writing I also mean when you write fast, sometimes we just keep on writing row vectors, but when you try to operate them, we operate thinking as column vectors. So, that would happen, specifically that happens when you write research papers and all, it does not matter, but here try as much as possible to keep up with a kind of bookkeeping, that whenever I am talking about a vector, I am talking about a column vector. But it is interestingly enough, a vector itself has here, for example, a vector in R n which has n components v 1, v 2, v n has got n rows and only one column. So, basically it should be, if we write, it should, this v 1 is a 1 1, then the next is a 2 1, the next is a 3 1, the next and the end is a n 1, that should be the thing. So, it is a matrix with n rows and 1 column. So, it is a n cross 1 matrix. Now, the question is what kind of operations we can do with matrices. For vectors we have seen we can add them, we can do scalar multiplication, we can take inner product. Now, matrices, for matrices we ask two simple things: can we add two matrices, does it make sense, what it means to add two matrices? And then we ask a more complex type of question, that because we know about inner product of vectors and matrices are stack of vectors, do we think that the idea of the inner product can be somehow brought into the zone of matrices? That is, can they be fruitfully used to talk about something which we can call multiplication of two matrices? This is a key idea, because multiplication of matrices is very, very important. A lot of things in science and a lot of things in numerical computation really depends on this whole game of matrix multiplication. It is a key idea. So, if you have two matrices A and B with entries of the form A I j and B has the entries of the form B I j, both has to be of the same odd size m cross n, same number of rows and same number of columns, then the new matrix A plus B is an m cross n matrix again, but their ith jth entry is now the ith jth in the addition of the ith jth entry of A and ith jth entry of B, that is the entry in the ith row and jth column is A I j plus B I j. Now, in the next step we are going to show that there is this concept of multiplying a matrix by a scalar. So, you are taught, if you have, many of you must have learned matrices, these are graduate level course. So, in undergraduates you will have learned matrices. You can think that this is just a fast recollection of what you possibly know, or maybe as you take a detour you will learn, pick up something new from the sides of the road. Now, if this is a matrix, say here it is a 3 cross 3 matrix, and I scalar multiply with alpha, then we have been taught when we were in high school or maybe in the first year undergrad that you multiply all these elements of the matrix with alpha. Why you think one should do so? Here a good explanation can be provided if I view a matrix A as a stack of column vectors, right. So, if these are the 3 column vectors which make the matrix A. So, when I multiply it by alpha, I am doing a scalar multiplication with this first vector, scalar multiplication with the second vector, and a scalar multiplication with the third vector, and scalar multiplication by definition is this, we scale up every component. So, that is it, and that is why you get what you get. So, here I have tried to motivate why that viewing matrices as a stack of column vectors, stack of vectors, and then you have to define alpha A is in this way, that is as if you are actually doing scalar multiplication of vector. So, scalar multiplication of vector and addition of two vectors are the fundamental things. Combining these two, what we get is something called linear combination of two vectors, alpha of V1 plus beta of V2, that kind of, and you can build whole your linear algebra just based on this concept. This is one of Gilbert Strang's first lines in his book on linear algebra, and that is absolutely true, because you can build the whole of linear algebra just sitting on this concept. That is called linear combination. That is absolutely truly fundamental to what you are doing, right. So, that's besides the point. So, once you start looking things just from that very, taking everything from that rudimentary view of the vector, then everything starts falling, making sense, even when you are in a domain which looks to be outside of the vector domain that you have studied in the last lecture. So, the next natural question is how to multiply two vectors. Now, this is the tricky point, because how do you multiply with a matrix, or how do you multiply matrix with a vector first, because vector is a very simple matrix, some number of rows and some number of columns. Now, what we want to do is we want to profitably use the notion of the inner product between two vectors and try to define what do I mean by multiplication. Please understand, we are trying to define something. Of course, you can say what is the motivation of such a definition and why not others. For example, if I can look it as a, suppose I take a V1, V2, V3 is a square matrix. I take it as a stack of vectors here. Look at the column vector and multiply, take inner product with this vector. Look at the column vector and take inner product with this vector. Look at the column vector and take inner product with this vector. Even if you do so, you are essentially doing inner product of two vectors and then lining them up as vectors. But the way we look at it is this, that when you write the inner product of two vectors, what do you mean? You write one of the vectors as a row vector, another vector as a column vector. If I say, if I take two vectors u and v, then you write the inner product as u transpose v, which means you multiply u transpose of u with v, and there is a way to define it, which you know, component wise. So, what happens here, if I have a 3 by 3 vector, the number of columns of this matrix has to be at 3 exactly. It can have more rows, does not matter, but the number of columns should be equal to the number of the number of components, the vector on which it is trying to multiply, act upon, be the same. Then only you can do inner product. But if you have a column 4 here, then here also you need 4 entries, otherwise you cannot do the inner product would be defined. So, if you have, if I call this vector v, which has components v1, v2, v3, and I call capital R1 is the row vector of this matrix, R2 as the second row of this matrix, R3 as a third row vector of this matrix, then the inner product of R1, which is A11, A12, A13 with V. So, that is when you do the inner product, it will become A11 V1, A12 V2, A13 V3, and that's the inner product of R1 with the vector V itself, right. So, the answer is you take the first row, take the inner product with V, take the second row, take the inner product with V, because these inner products are fully defined, well defined, because the number of columns here matches the number of rows here, rows of the vector V, and take the third one and write R3 into V. So, you see, knowing once you have inner product, you can build this simple idea of a matrix acting on a much simpler matrix, that is n cross 1 matrix, which is a vector. So, that's done for you, right. So, the operation AV is given as follows. So, what is the rule? Columns of A are same in numbers as the rows of V. This is a key rule, and AV is nothing that if R1, R2, Rm are the rows, you can write them as capital also, as I have written, just writing it for the sake of just I have written it, maybe I did not even recall what I was doing when writing. This happens quite often because you just focus on what you want to say, and symbols have lesser meaning than what the thing that been actually been told. Here R1, R2, Rm are the row vectors of A, which is an m cross n vector, and A into V which is a n cross n1 vector. So, this is the answer, this is what would happen. So, this is how the operation is defined. So, using inner product or dot product, which we learned in the last class, we can actually define how a matrix would be multiplied with a vector, and this can be also viewed as a matrix as a function operating on a vector. But this function, if you view matrix as a function, we will have a typical property which we will call linear functions, and that we will learn as we go on in the fourth lecture that would come up, and we will show that in finite dimensions, that in the spaces that we know R2, R3 and whatever, the only possible linear functions are vectors, are matrices. So, we sometimes would like to call the matrix A as a transformation, we will later on call it a linear transformation. Transformation in the sense that when a vector A acts on a vector, when a matrix A acts on a vector V, it transforms the vector into a new vector. So, it is an m cross n matrix with n cross multiplying an n cross 1 vector, giving me an m cross 1 vector. Now, I have m rows in this new vector. So, the vector V, the original vector V is transformed. So, the matrix A carries an element in R n into an element in R n, and that way the matrix A can be viewed as a function mapping elements in R n to elements in R m. So, mappings between vector spaces are often called transformation. These are all names which has some geometrical meaning, of course, but for us at this moment these are names of our function, they are functions at the end. So, there is a very different way to visualize AV, this operation, and that will be it will be shown that this AV is nothing but a linear combination of the row of the columns of the vector A with respect to the components of the vector V, and this is very fundamental. When you can write down this operation AV, this way of looking at AV, what we will now discuss through linear combination, tells you how actually this matrix A operates on the vector V. This actually shows the operational part. Earlier it was like a multiplication we are doing using the idea of inner product, which we know a kind of multiplication between two vectors, and then using that to create a new vector, and from that we get the matrix is carrying elements in R n and pushing them into elements in R m. But how does it do that job? How does it push? What is the mechanism of that pushing? How does it take up an element in R n and throw it to an element in R m? What is that mechanism of carrying it from one vector space to the other vector space? That mechanism will now be described, and that will be done through the notion of linear combination. So, if you have V1 hat dot 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 V hat k elements in R n, then a linear combination of the above vectors with respect to certain scalars alpha 1 to alpha k. So, these are real numbers for us and nothing else, is the vector alpha 1 V1 hat k, that is you multiply each of these vectors by the corresponding scalars V at I with alpha I, and then add them all over, add all of them together as vectors. So, alpha 1 V1 vector plus dot 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 alpha k V k vector, and that vector has to be in R n, of course. So, this is called a linear combination. Now, let us take a 2 by 2 matrix and a 2 by 2 vector V. A is a 2 by 2 matrix, has the first row is given by A11 and A12 and the second row is A21, A22. What we have just learned, then doing the inner product of the first row with the vector V here, I will get this component A11 V1 plus A12 V2. Then for A21 22, I will get the components A21 V1 plus A22 V2. Now, I can view this whole thing as a sum of two vectors. What are those vectors? A11 V1 plus A11 V1 A11 A11 V1 A22 A1 V1 A11 A21 V1. This is one vector. This if you have added with A12 V2 A12 V2 and A22 V2 with this vector. If I add these two vectors, I will get this vector. So, I can write them as V1 A11 V1 A21 plus the vector V2 A12 V2 A22, but you know by the definition of scalar multiplication I can write the vector outside V1 and V2. So, by what you have just learned, this is nothing but a linear components of the rows A1 and A2, columns A1 and A2. So, the matrix multiplication can be is nothing but a linear combination of the column vectors of A, where the first column is scalar multiplied with the first component of V, second column is scalar multiplied with the second component of V, third one is multiplied with the third of V and so on. So, this is the mechanism. For example, here the first component has first row column has two components, is the vector in R2. Second one has two components, the vector in R2. So, when you multiply by with the two scalars, you take a linear combination, you will have a vector in R2. So, a square matrix takes a vector from the same given whatever space and say Rn and takes it and pushes it to Rn. The mechanism by which it does is computing this linear combination. This is the inner mechanism of the function, that how it actually transforms this vector in some Rn into some other in Rn. For example, if I had another row here A31, A32, then I would have this would become V1 A11, that is V1 into A11 and this whole thing plus V2 into A22. So, there was V1 into an element in R3, V2 into an element of R3. So, it would have taken a matrix from R2 to R3. So, it was a 3 cross 2 matrix into operating on a 2 cross 1 vector, multiplying a 2 cross 1 vector. So, basically the trick to keep in mind is to cut off these equal rows and columns, the rows of column number of the matrix and row number of the V, and keep the row number of the final matrix or final vector, keep the row number of the matrix and column number of the vector. So, ultimately if I had another row, I would have been doing a linear combination of two vectors, but those two vectors would be in R3 giving me a vector in R3. So, I would have taken a vector in R2 and put it in R3. So, a 3 cross 2 matrix multiplying on a 2 cross 1 vector gives me an element 3 cross 1 vector, which is an element in R3. So, this is the mechanism by which you are taking an element. So, the lot of things are coming together. So, here is the use of inner product to tell how a matrix can be multiplied with a vector, and then telling the mechanism by which you multiply. Now, this allows us now very simply, once you know this allows us to simply operate out the definition of how to multiply two matrices. Now, you will immediately understand one of the key rules is that the number of, if I want to multiply A into B, A is my left hand matrix and B is my right hand matrix, then the columns of A, number of columns of A must match the number of rows of B. Because if I want to do this matrix multiplication A B, then These are considered the column vectors of B is written as small b1, b2, bk. So, B is say n cross k matrix and A is an m cross n matrix. Now, B1, the number of rows here must be same as the number of columns here, that is n, and then A B is defined as A multiplied with the first column vector of B, A multiplied with the second column vector of B, A multiplied with the kth column vector of B. Each of these new vectors are the columns of the matrix A B. Now, again I know if R1, R2, R3, Rm are the m rows of A, then and A of B1 in by what we have defined earlier is nothing but R1 B1 dot 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 Rm B1. For example, the kth matrix here R1 Bk, kth row here, kth column here R1 Bk, Rm Bk. So, m cross n matrix multiplying an n cross n matrix would give me an m cross k matrix. So, AB has m rows and k columns. So, you see what we did here, we have defined matrix multiplication in this way, and once we have done this, we know how to compute each of these, and that is what happens. So, immediately you see just the very notion of dot product can now allow me to define the element of a matrix. Let C be equal to AB, let C be equal to AB, A into B. If I write the matrix AB as C, and if the ith jth element is called Cij, then Cij is obtained by taking the dot product of the ith row of A with the jth column of B. This is the game. For example, here I take these two square matrices and I want to get the this entry in C, which is the second row but first column. So, I want to talk about A 2 1. So, I have to get the second row of A multiplied with the first column, taking an inner product with the first column of B, that is 0 into 1 plus 2 into 3, which is 6. Similarly, you can fill up all of these. So, with this description till now, we are going to end our discussion for the first part, and we will go into several other things in the second part and tell much more about matrices, and I am sure that will equip you with the tools that you now require to explore linear algebra and many other things. Please understand that what we will study in linear algebra has its implications even in studying modern analysis, which is an extremely important requirement for economic sciences. So, with this I would like to close the first part of lecture 2. Thank you.